So let's recap a little the radiation balance that we are looking at. Essentially, we took the surface and said there is a net short wave coming in. It depends on the albedo, and the surface emits long wave, which is obviously sigma surface temperature to the fourth. But how is the surface temperature determined? If you put a layer of the atmosphere, then whatever long wave is going back from the surface is going to be absorbed by the greenhouse gases, which themselves will emit long wave in both directions, which will depend on the temperature of the atmosphere. So the balance at the surface has to include what is the short wave that come in to heat the surface and the long wave that's coming from the atmosphere. So we are using atmospheric temperature and emission temperature as the same, because we are assuming one layer, and that layer of the atmosphere is emitting to space. So if we plug in for the short wave part of it, when we did the balance, we get this equals sigma Ts to the fourth equals 2 sigma Te to the fourth. And we said one of the most important concepts is that a greenhouse effect gives you surface temperatures that are warmer than the emission temperature, because this is greater than 1. You can complicate things by adding emissivity, where the surface is not perfect emitter, which means it's not a perfect absorber. Atmosphere is not a perfect emitter, hence not a perfect absorber, and the atmosphere can absorb some of the short wave radiation and so on. But nonetheless, the story is that greenhouse effect can produce emission at a colder temperature and produce a surface temperature that's warmer. And in this case, if you plug in the numbers, you will get surface temperature of 303 degree Kelvin or 30 degrees centigrade. Obviously too warm, because we know that the average temperature of the earth is around 15 degrees centigrade. So without any atmosphere and greenhouse effect, we had very cold temperatures. By adding one layer, we have made it very warm. Clearly situation is more difficult. The atmosphere, remember, the lapse rate is something like this. So the atmosphere has many layers, especially in the stratosphere. So there is energy bouncing around between the surface layer above it and the layer and so on. Okay? Does that give you a better estimate? You will get closer, but still not accurate. Why? Because clearly this is what is called a radiative equilibrium, where short wave is coming out, long wave is bouncing around and eventually going out. But we know that the atmosphere has motion in it. There is winds moving, there are clouds forming, there is convection happening, air is rising, and so on and so forth. So the atmosphere is actually in what is called a radiative convective equilibrium, and not just a radiative equilibrium. That makes life much more difficult. We won't get into all the details, but let's recap the long wave and short wave again. So this curve, which shows the distribution of radiation with wavelength, is the so-called Planck function. So the temperature at which a body emits decides its distribution of wavelengths. Sun is producing its own energy through nuclear fusion. Temperature is more than, it's about 5,760 degrees centigrade. So it is all white. We can see that it's white. So think of a iron that a blacksmith is heating. When it starts heating, it's still black, but as he keeps on giving it more energy, eventually it can become red or white. So the temperature of the body determines what wavelength at which it begins to emit radiation that it is absorbing. So the full electromagnetic radiation is given in this yellow curve, and there is something called the Wien's law, which you can read up about. It's W-I-E-N. Wien's law basically takes the spectral distribution with wavelengths and computes a maximum, the temperature at which maximum energy is produced, and then fits the curve so that the area under this curve is equal to the total energy being produced. So the yellow curve and the smooth black curve here have the same amount of energy coming out. That's just a detail. So this is the black body spectrum for 5250, which can be computed easily. Okay. So, the red curves here are the various gases in the atmosphere that are sensitive to incoming short wave radiation. When we did the radiative equilibrium calculations, we said atmosphere is allowing all the energy to short wave energy to go to the surface. Obviously, it is a simplification. Ozone, we know that is a greenhouse gas, and it is also sensitive to short wave radiation. Oxygen in the short wavelengths where UV occurs, obviously oxygen is being bombarded, split into atoms and combining with another oxygen to form ozone. So, it is sensitive there. So, you can see that there is a high level of absorbance there, absorptivity there at shorter wavelengths. Then you have water, which is also sensitive to short wave, and CO2, etc. So, you can see that water has multiple wavelengths, and several gases have multiple wavelengths where they are sensitive to either short wave or long wave. So, it just depends on how the quantum physics of that molecule works. Typically, symmetric molecules like O2 and N2 are not sensitive to short wave or long wave. So, they are not greenhouse gases. Good news, because there is a lot of nitrogen and oxygen. If they were greenhouse gases, we would warm up like Venus. But CO2, which is symmetric, actually has a bending mode. So, it is sensitive to long wave radiation, and this energy then 75 to 80% makes it to the surface beyond what is reflected already by albedo, and the earth then begins to emit as black body radiation. First thing to note, this is in nanometers, that is 10 to the 9 meters, whereas this is in micrometers, so that is 10 to the minus 6. So, this is about 2.5 micrometers, so that is somewhere here. So, the radiation spectrum of the sun and the earth are completely separated. So, if you put sun, it will be somewhere here. Okay. So, that is the again the Planck function or the Wien's maximum temperature distribution, and you can see that now the absorption of the outgoing long wave is very strongly affected by ozone, water, carbon dioxide, and so on. So, this is what the essential greenhouse effect is. So, after Svante Arrhenius said CO2 is going to affect Earth's temperatures and global warming is going to happen, he did not use the term global warming, but nonetheless there was a mistake made by Angstrom, the son of the angstrom whose name is associated with the unit of length we use, angstrom. So, he made wrong claims that CO2 is actually saturated and increasing CO2 is not going to affect energy balance, because he assumed that the water and CO2 are in the same band, water will increase, CO2 will increase, and radiation will not be affected, radiation balance will not be affected. Some people still repeat this mistake, but it is completely wrong. CO2 and water are close to each other, but they are not overlapping. So, if you increase CO2, indeed you will have increased greenhouse effect and greenhouse warming as we are observing now. So, what does this mean in terms of actual realistic radiation balance? Let us look at some observations from satellite for a particular month, April 2001, the reflected short wave at the top of the atmosphere and outgoing long wave at the top of the atmosphere in watts per square meter. So, reflected short wave is obviously related to albedo. We said it is on average for the whole globe is 0.3. Obviously, it is distributed. So, it depends on where the clouds are. So, you immediately see that where the Hadley cell goes down and there are high pressures and clear skies, the reflected radiation is low, and where the ITCZ is where there is rainfall and lots of clouds. Clouds grow tall and the top of their reflectivity at the top will be very bright. So, they reflect large amount of sunlight. At high altitudes, high latitudes towards the poles, you have another convergence zone, which we looked at, we will look at it again, and you have snow and ice and so on. So, wherever there are reflectivities due to vegetation, clouds, high content in water vapor, whatever, you will have high solar reflectivity. Deserts unique because they can get very warm during the day, there are no clouds, so you heat with the solar radiation, but deserts can also have high albedo, and at night they can lose long wave radiation a lot because there are again no clouds to block the outgoing long wave radiation. So, this already begins to tell you that outgoing long wave radiation is also going to be a complex story. There are high outgoing long wave where there are no clouds again, and where there are clouds, the cloud top temperatures are going to be cold because as we go up in altitude, the temperature drops, and that is true for also cloud top temperatures. So, clouds do not emit so much outgoing long wave radiation because of reflectivity. They reflect solar radiation, but they do not emit sigma t to the fourth is small because t is small. Okay. So, that begins to tell you that the balance is going to be much more than just the kind of simple radiative equilibrium calculation we just did. And you can see that with this simple animation of the seasonal cycle, we looked at the short wave radiation before, and we are now showing the long wave and the net radiation. You can observe it more carefully, but essentially as the sun moves, maximum radiation, maximum short wave radiation occurs in the summer hemisphere, and associated with that you have corresponding changes in long wave radiation, where the clouds are low long wave radiation, where it is clear high long wave radiation, and so on. So, the net energy balance has many interesting features that you can look at. As I said, the deserts like Sahara Desert actually can have net negative. So, they can have an energy loss. So, they are receiving lots of solar, but they are also emitting a lot of long wave radiation. So, they can actually be losing energy, like the higher latitudes where albedo loss is so high that received solar radiation is low, and the outgoing long wave, even if it is low because of low temperatures, you have deficit in energy. So, those are the kind of things we have to watch out for. So, we will come back to the impacts of global warming on these kinds of issues, but this is kind of a good point to look at little bit more details of how the radiation balance works, because we must always put it back in the context of greenhouse gases. So, if you look at the flux in watts per meter squared versus the wave number at various temperatures, then you know that the earth is emitting from the surface and various levels of the atmosphere, including the clouds. So, the deserts have clear skies, so outgoing long wave can directly go to space, but from places which are rainy or have lots of clouds, outgoing long wave cannot go back directly to space. And the CO2 concentrations in the atmosphere are not uniform. So, the temperature profile on the other hand is generally maintained in this shape. So, then the critical question is, where is the emission from the earth really happening? If you go out in space and look from a satellite, you can always compute an effective emission temperature, but where is that emission happening from? That is not a very easy question, because it depends on where the emitting greenhouse gas is. Okay, the CO2 band here, so it is a spike here, there is an ozone spike here, and H2O has multiple bands, and here is CO2 band, and so on. So, everybody is emitting at a different temperature. So, this is from a satellite measurements, and this is from a radiation model. So, the climate models have all the gory details of radiation physics. It is a very complicated calculation, and it in fact takes the most amount of time. If you think of ocean circulation, atmospheric circulation, clouds, etc., radiation module takes enormous amounts of time, because you have to calculate all the bouncing around of the calculations. So, that shows this complicated emission spectrum from earth, and in a simplistic sense that means obviously from the surface there is outgoing long wave like in the deserts, but everywhere else but whether that gets absorbed and bounced back or not depends on what is above it. But the effective emission happens somewhere around 6.5 to 7 kilometers, and what temperature it happens at depends on various things like where you are on the planet, because the temperature at 6.5 kilometers will be very different in the tropics compared to the subtropics or mid latitudes or the polar regions. Okay. So, to explain the balance to your students, you will have to invoke the fact that the atmosphere has very strong convection in warm temperatures and at higher latitudes where there is again convergence and rainfall. If you remember, we have two rainfall bands, the tropical convergence zones and the mid latitude storm tracks or rain bands. So, that means it is not just radiation, you have this convection which is also moving around energy and emitting at different temperatures. Then the question is, how does that 6.5 kilometer change with global warming as we increase greenhouse gases and change albedo and so on and so forth. So, to re-emphasize, 340 coming in, 342 give or take, 30% is emitted back, reflected because of albedo. About 240 is arriving in the climate system. It's bouncing around and creating much higher levels of energy because it's the blanket of the greenhouse gases. But 240 must go out because at the top of the atmosphere you still have balance on a yearly time scale or a multi-year time scale. You cannot keep building energy, but that means that you have to somehow emit that energy at a different temperatures. This is why we said greenhouse can give you a warmer surface and the emission temperature can be different. So, how do you do that? So, essentially you have 150 watts per meter squared of natural greenhouse effect, and the enhanced greenhouse is right now trapping some additional long wave radiation that should go to space, but it's being trapped, and the outgoing is balancing the incoming, but it's being done at a different temperature. That's what I want to emphasize. How does it do that? Basically, this is a simple animation from Bernstein, which shows that as the greenhouse gases increase the amount of energy trapped or being bounced around. So, I should always be careful. Increased amount of energy trapped tends to mean that we are not losing 240, we are losing less than 240. That is not true. So, we are still balancing at the top of the atmosphere, but internally we are adjusting things because of these dynamics with which the atmosphere can move energy around and emit at a different height. So, this is what happens, and there is evidence for this, that the tropopause at which the sign of the temperature gradient changes. So, troposphere, tropopause and stratosphere, that begins to increase in height. So, you are putting more energy into the system and that is expanding the air column. Okay? That is how you have to essentially explain the greenhouse effect. Sounds complicated, but go back and listen as many times as you want and you will see what I mean. So, how does the tropopause change? Going back to some of the fundamentals, we know that in the tropics tropopause is tall because you have warming, rising air, clouds, temperature is being pushed up. In fact, it is pushed up so much that the cloud top temperatures here can be actually colder than the temperatures in the subtropics, which is obvious in this figure here. So, you can see that outgoing long wave here is lower than here, which means at the top the sigma T to the 4 here is lower than here, because the clouds are rising so high that the cloud top temperature is colder. So, because of various dynamic reasons, where the Hadley cell meets the so called Ferrel cell, you get a jet stream. I think you know what a jet stream is. It is a very fast concentrated river of air that is moving at 30, 40, 60 miles per hour, and there is one in the subtropics, there is one much more powerful one in the polar latitudes called the polar jet. This has lots of impacts on the weather and climate of the higher latitude places like Europe and US. So, this is again where rain is possible because the polar cell meets the Ferrel cell. So, Ferrel cell is going this way. So, this long story short, the tropopause actually drops as you go from the tropics to polar latitudes. So, the where the tropopause increases most and where it doesn't depends on these kind of dynamic adjustments. So, as you increase greenhouse warming, tropics should get more evaporation and more rainfall and so on. So, the vertical motion and the tropopause height will increase. As it subsides here in the Hadley cell, more complicated things happen because the warming is also able to expand the tropics, which means the Hadley cells themselves can expand. I am just saying these things jumping a little bit ahead because it is a proper place to begin to introduce the concepts of how global warming begins to manifest itself. So, we are kind of coming to the end of the radiation forcing and radiation balance and moving towards what the impacts are of global warming. So, let us look at this with a kind of an animation with some more information. So, we have solar radiation input and emission to space with all the complex convective dynamics that is happening inside, and we have these various greenhouse gases. So, greenhouse gas CO2 concentration obviously has increased and is expected to continue to increase, and here it is in parts per million. The whole struggle with IPCC negotiations and so on is where is it going to cross the dangerous levels, right. So, if you look at the resulting greenhouse gas warming that we have already looked at, this is what we have seen before. We will see this graph again and again and add more and more information to it. So, we will have to essentially come back and explain why these ups and downs happen even as the warming happens. I think you already know the answer, that is the internal variability. Okay? That is in a simple way to look at these things, but let us look at additional information of how the lifetime of things also matter. So, carbon dioxide has a lifetime or a residence time of 50 to 200 years. Residence time is a scientific word which has a definition and there is a way to calculate it. You will have a separate module on it, but intuitively once you put it into the atmosphere or water, how long does it stay? That is kind of the residence time. So, we typically say CO2 as a baseline. So, it has a global warming potential of 1, whatever the watts per meter squared change it makes and whatever the net warming that happens, that we assign as value 1. Methane has a much shorter residence time. It is highly oxidizable, but it is 21 times more powerful as a greenhouse gas than carbon dioxide. We know the sources already, so I won't emphasize that too much. Nitrous oxide has a long time scale and is tremendously powerful as a greenhouse gas. Why do we care? That means once you put these stuff into the air, they can stay there for a long time. Even if we suddenly wise up and say we are going to stop all the pollution, your children, grandchildren, great grandchildren, great grandchildren will all be experiencing the continued warming if these gases continue to create global warming into the future. Hydrofluorocarbons lifetime depends on the particular species of it, can be very short like 1.5 years to more than 200 years, and the global warming potential can be 11,700 times the carbon dioxide. That is shocking because remember HFCs came to replace CFCs because CFCs were creating ozone hole. So we are always doing these kind of experiments which are called Frankenstein experiments, where we think we are doing something good, then we create another monster. So HFCs will quickly have to be replaced because they have huge global warming potential. They are deadly global warming agents. Perfluorocarbons can stay for up to 50,000 years, and they are 6,500 to 9,200 times CO2 in their global warming potential. Sulfur hexafluoride comes from electric power transmission and semiconductor industries. This comes from aluminum production and semiconductor manufacturing and so on. This has almost 25,000 times the global warming potential, and it can stay for 3,200 years. All the industrial development, scientific progress, everything comes from these things, right? So we always have to be careful where the energy is coming from, what we are doing in terms of the materials we are using for our comfort and our progress, and so on and so forth. And in terms of motivating students, you know that this means there are so many opportunities to look for solutions. How do you produce semiconductors, transmit electricity without relying on harmful substances, or produce energy in a completely different way, etc., etc. So the global warming is a huge challenge, but in terms of a green economy, maybe you can portray it as a monumental opportunity. Either way, it's a biggest challenge humanity has faced since it became so powerful in the last 10 to 12,000 years. Let's briefly put this together in the context again, going back to the end of the last glacial maximum. CO2, huge increase. Nitrous oxide, huge increase. Methane, huge increase. And the difference from before is that in this case we are also showing the radiative forcing, and in this case the rate of change. Okay, so and the radiative forcing is on this side. So we are definitely beyond any natural variability at this point, and compared to what time period depends on what you are looking at. We are definitely beyond the deglacial time since the last 20,000 years. Looking at Antarctica, CO2 levels are definitely beyond the last few million years, and so on and so forth. We have to always keep those things in mind. So we started with the context for global warming in terms of sea level and natural variability. We went through detailed information on radiative forcing and brief introduction to carbon cycle and radiative balance, and showed the complications of how increased greenhouse gases changes the emission temperature and energy balance. Key thing to remember, it's not just radiative equilibrium, it is radiative convective equilibrium, which complicates life quite a bit, as we will see when we look at the impacts. So let's start looking at the impacts. How do we do that? So we have been looking at paleo data and some historic data, historic records, and obviously now we are relying more and more on instrumental records. So I will just give a sampling of what are the various data sources that are there. So ocean is now pretty much covered. You can see here there is a global time series network, which means some things are moored in the ocean and they stay there for a long time, and they continuously record temperature, salinity, currents, winds, and sometimes oxygen, chlorophyll, light, and so on and so forth. And there are obviously surface ship measurements, and there's a network called volunteer observing ships, and there are these lines running across the globe. So all the trading that happens between different countries and continents and so on is done through these container ships, cargo ships, passenger ships, and so on. All of them are equipped with some kinds of instruments, or what are called expendable bathythermographs and so on, which something they just throw overboard. It's a coil that unwraps and measures temperature as it goes down to 500 meters, sometimes more than that, and so on. There is a moored tropical network. So, these black dots here in each ocean, in the Indian, Pacific and Atlantic Ocean, they remain there and they beam the data to satellites. So, this is like a satellite antenna here. So, you can see this is a kind of a profile with a satellite antenna at the top, and this is now the most recent and amazingly innovative idea that started at the Scripps Institution of Oceanography, which is here, and it is called Argo Float, ARGO, and essentially it has various instruments. So, it has a bladder so that it can go up and down, and it has the hydraulic fluid which changes between chambers, its buoyancy can change, but it measures. It started with just trying to measure temperature, but nowadays it also measures oxygen and other things. So, it is called a biogeochemical sensor, and the beauty of it is it goes down and stays at 1000 meters or at 2000 meters for many days, and every few days it comes up. As it comes up, it measures whatever it wants to measure, comes to the surface, sends the data to the satellite, which can immediately be seen in the lab wherever you are sitting on the computer, and then it goes back down. Why does it go back down? Basically because near the surface the currents are too strong, so it will drift if it does not stay in the same place. But as you go deeper into the ocean, remember the thermohaline circulation is very slow, like a molasses, hardly moves centimeter per month or two, whereas near the surface you have a centimeter per second. So, it stays there and does not drift too far from where you want to be. So, these are kind of the distribution of the Argo arrays. The other big reason is that anything that you put near the surface becomes what is called FAD, fish aggregating device. So, things begin to grow on it, biology immediately begins to attach to it, barnacles and so on, then other fish come nearby, and soon the instrument will be covered with so much biology that it will not be able to measure anything. That is called biofouling. So, some of the things that are forced to remain near the surface often use various methods to avoid biofouling, sometimes like putting poison. Sounds harsh, but you have to do that. Human beings, we want what we want and we will get rid of everybody else. So, that is another reason. Remember, there is hardly any biology at 2000 meters. So, if it stays there, it does not drift and it does not have biofouling. So, that is a phenomenally new observational system. Plus, since the 70s and 80s, the number of satellites that have gone up has been increasing by a large number. Lots of international operations, they can measure winds, chlorophyll, humidity, carbon dioxide, ozone, carbon monoxide, sea level change, vegetation, sea surface temperatures, and so on and so forth. Okay. On the ground, you have ground stations from 1890 to the present. They have increased in number constantly, and this is the latest one. You can see how extensive the coverage is, plus the length of the records. Some of them are now almost 150 years long. Some of them here that started during the British time have been collecting data for 150 years. Many are 50 years long, and there are some that are brand new that are just starting, especially in the Arctic and at higher latitudes in the Antarctic and Southern Ocean as well. So, it is very important to keep collecting data, because any confidence we have in claiming trends or global warming or changes must be based on the data that we have. So, the ocean instrumentation, going back to the 1950s, actually there are ship reports even from the 1870s when the Challenger expedition happened. You can look it up. Challenger expedition was one of the first planned scientific expeditions which carried hundreds of people with a lab in the basement where people were collecting water samples, logging the types of phytoplankton, zooplankton, and so on and so forth. But lot of the enhanced instrumentation started after the Second World War. During the Second World War, there was data collected, but it was hidden or kept secret because they wanted advantage over the enemy and so on. So, there were things like the MBT, which was the bathythermograph that was different than the so-called XBT, that's a new one, and now we have deep XBTs and shallow XBTs, and we have also called something called CTD, which is, so XBT is expendable bathythermograph, CTD is current, temperature and depth. Current means what? Amount of salinity or salt in the water determines its conductivity. So, conductivity, temperature, depth gives you salt, temperature and the depth at which the measurement is made. So, the MBTs died away, old technology. These are the bottom measurements, and the shallow and deep XBTs and floats have now increased in the last part almost exponentially, as we saw in this figure. So, this is an excellent way of collecting data, because a ship per day can cost up to $100,000. That's a lot of money, right? More than 2.5 crores, I think, in rupees. So, that's a very efficient way. So, another idea for students if who want to work on climate change solutions is use technologies like robots, drones, solar batteries and so on to build instruments to measure things far away in the ocean. In the middle of the ocean, it's hard to go all the time, but if they can invent things, then they can be super rich and do something very good for the planet and humanity. How has the amount of data changed? So, this is showing 5-year chunks of data from 50 to 55, 55 to 60 and so on to 2005 to 10. These are the number of profiles measured in the ocean. You can see that in the 50s the traffic was high between US and Asia and Europe and US and some other countries here, but over time the network has expanded. Especially you can see here hardly anything here, but suddenly there is a big boom, and now the entire ocean is quite heavily covered with profiles that are measured. This is worth re-emphasizing. Why do we need profiles? Remember that the satellites can look at the surface only. Anything that satellite is looking at, whether it's a radiation coming from the surface or the laser it is sending down and measuring the return, it can only penetrate few centimeters to a few meters. The ocean is several kilometers deep, and this is very important because we said thermohaline circulation can take down the heat and the gases and so on and put it down there. So, we must measure the profiles in the ocean. So, this is very critical, and this is now facilitated heavily by the Argo floats. So, amazing stuff happening, right. So, what are the effects? Let us start with global warming. The canonical picture for global warming compared to the canonical picture we had for carbon dioxide has been this figure, which shows the global mean temperatures. Sometimes it goes back to 1850 or so, but nonetheless about beginning of the industrial revolution to the present. What does it show? Compared to the baseline data of typically the baseline climatology from which the anomalies are computed is chosen to be something like 1961 to 1990. So, the temperatures before the 1940s or so were colder, then they began to jump around a little, and since the 1970s they have basically begun to warm, and seems like the rate of warming is increased, but you can see that here maybe there is a kind of a flattening. We will come back to that. So, you can see that even when it was cold it jumps around, even when it is warming it jumps around. Why? Obviously internal variability. El Nino throws out heat from the ocean, La Nina soaks up heat from the atmosphere. So, volcanoes go off, they produce a global cooling. So, these internal variabilities and natural forcings will not go away, and that produces these up and downs. So, that is always something to understand. If you look at the map, again remembering that the data coverage was poorer as we go back in time, you can see that the warming is not uniform. Why? Just like radiative equilibrium, There are places where convection happens, cooling happens. There are places where ocean can take up the heat and move away. There are places where ocean can soak up the heat, so doesn't have to warm so much because the Ekman divergence and upwelling keeps bringing cold water, and so on and so forth. And there seems to be very little warming or maybe even a little cooling in our favorite region, the so-called Gin seas or Greenland, Iceland, Norwegian seas or the North Atlantic. As soon as we say Gin or North Atlantic, you should jump on it and say thermohaline circulation. So, if the meridional overturning circulation changes in a way that it reduces the amount of heat being brought in by the Gulf Stream, then potentially there can be less warming or even a cooling over this region. Obviously, you have to watch it carefully, because if thermohaline circulation gets perturbed, we know that a lot of other things can go wrong. And this, not enough data in this region, but in general you can see that the tropics are warming a little bit less than these higher latitudes. There are many things involved here, but briefly, the tropics are already pretty warm. If you try to warm them more, the air will rise and it will rain, so it will start convecting more. Maybe there will be more tornadoes, maybe there will be more hurricanes, we will see that, more cyclones. So, the tropics tend to create lots of climate perturbations or climate extremes when you try to warm them, as opposed to high latitudes where you have ice, snow and other things which can begin to have ice albedo feedbacks and so on and so forth. So, this warming, larger warming at higher latitudes is called polar amplification. So, the global warming has a polar amplification. Okay? That is because of this ice albedo feedback and the differences in dynamics. So, how the climate responds depends on what is the regional dynamics. This is very important. So, you can now go back to think about your radiation balance. We were doing some simplistic calculations which do not hold anymore, because the energy is being moved around. And the other thing to remember, of course, is that when we introduced climate, we said the equator to pole temperature gradient is important. So, if we warm the higher latitudes more, that means we are reducing the equator to pole temperature gradients with global warming. This is going to affect the entire circulation, the Hadley cell, the polar cell, the Ferrel cell and so on. Large scale dynamical changes are going to happen because of this. Amount of energy moved that has to be moved changes, which means thermohaline circulation and the entire circulation system changes. I like this figure because now we are putting together the carbon dioxide and the warming together. We said carbon dioxide is well mixed, can be measured precisely and accurately in 1 or 2 locations, and we have a very good sense of how much we have been increasing it. But temperature is very non-uniform to begin with. Tropics are warmer, mid latitudes are cooler and poles are colder, and the warming is not uniform. So, making a global mean temperature often does not have much meaning, because nobody lives in a global mean temperature anyway, but it does give us some sense of how the energy balance may be working. So, lot of the confusion raised by people who do not believe in climate change and so on comes from saying, look at how the CO2 is increasing, but the temperature is going up and down. You should not get confused, because that is not the real story. The real story is that the dynamics and the natural variability will always keep making the global temperature go up and down, but the trend continues. But we do have to explain, if a slowdown happened, why did it happen? Is it natural variability or is it something else? And remember that as CO2 increases and global warming happens, energy can go into the ocean and hide, but energy can also go to melt the glacier and does not show up as global warming. So, we have to also account for the energy that is getting lost in melting the glaciers. So, that can also temporarily reduce the warming or flatten the warming and so on. So, never get confused by people who tell you incomplete stories, non-scientific stories, and so on. The more you understand the complete picture, the more handle you are going to have on how global warming actually works. This is just a nice animation that shows that when we started in the 1800s, anomalies with respect to the present climate 1961 to 1990 were mostly cooler with some warm patches, but as we come into the 1970s, 80s and so on, you can see that other than this region here, everywhere else temperatures are just beginning to warm. So, you can now see that there is warm temperatures almost everywhere except in a few spots. So, it is important to understand the regional trends, because it depends on what your region is doing. All global warming is local. You want to know what is the impact of global warming in your backyard. But we will see that what happens elsewhere can be important for matters like human health, national security, and so on and so forth. So, you can look at this animation and try to figure out the polar amplification, which becomes very clear here as we come into the later period. So, you can see very warm here compared to here, very warm here compared to there, and so on and so forth. Okay? So, let us keep looking at this figure in many ways and make many different points each time. Okay? So, here is the linear trend in global mean temperatures for the past 25, 50 and 150 years. Why do we do that? Essentially to see that the rate of warming per decade is quite high in the last 25 years compared to the last 50 years or compared to the last 150 years. That means the warming trend since the Industrial Revolution is barely about 0.05 degrees centigrade per decade, but as you focus more and more on recent times, the rate of warming is accelerating. This is something alarming. This is consistent with the radiative forcing and the greenhouse gases we looked at, N2O, methane, carbon dioxide, ozone, etc. They are increasing at a higher rate and the warming is also keeping up with it. That is something very important to remember. And when somebody says, oh, this is such a small 0.2 degrees centigrade per decade, how much is that? Well, you take, let us say, water at a planetary scale, how many liters that is, you increase its temperature by 0.2 degrees centigrade and you compute the amount of energy that corresponds to. How much 0.2 degrees centigrade warming of all the oceans corresponds to? That energy is more than all the electricity produced per year for the whole planet. Okay? You can convert it to number of nuclear bombs and so on, but for peace sake, we will just look at the amount of energy we produce. That is how much energy we are accumulating in the oceans, atmosphere, land, melting glaciers and so on. So, do not just go by how small the numbers look, but see how much energy that corresponds to. That is something you can get your students to do as a back of the envelope calculations in terms of terajoules or kilowatts or whatever favorite units you want to use. So, this is another nice figure which shows the same global warming with respect to 1961 to 1990, different estimates, but this is also showing warming over land and sea and just the global sea surface temperatures or just the air temperatures over the ocean and the temperatures over land. So, essentially the warming is showing up everywhere. Air is warming, land is warming, ocean is warming. Of course, it matters how deep the heating is going into the ocean, which we will look at as we come to this topic more and more. So, the global warming signature, again to look at the same figure in the context of the change over last 1000 years or longer, we must always be sure that we are beginning to be significant, that the signal is now emerging out of the natural variability. We have already done that a few times, but again looking here, this is showing years going back from the beginning to the present. Northern hemisphere, these are the reconstructed temperatures we have been looking at with larger uncertainties as you go back in time. These are the different estimates, just northern hemisphere or just the instrumental period since the little ice age or so. No matter how you look at it, the warming is now beginning to emerge out of any range of warming we expect from natural variability. This context is important because if we keep calling it global warming, then we have to be sure that at least with respect to our own historic period, it is really unusually warm. Okay? The brief volcanic coolings that happen, natural variability falls into this. So, the same figure again being shown, but now showing with the volcanic eruptions that happened. So, Katmai 1926, that is a strong El Nino, strong El Nino, strong El Nino, the Pinatubo eruption, El Chichon eruption, Ogung eruption, and as we expect, when strong El Nino happens, there is a local spike in warming. When a strong eruption of volcano happens, there is a local cooling, local warming due to El Nino, local cooling due to volcano, and so on. So, natural variability produces these ups and downs in global warming. We always have to be able to remember that. So, global warming happens does not mean natural variability goes away, because the sun is still going up and down, sun is still going north and south, and ocean is still storing heat and releasing heat, glaciers are still melting or growing depending on what is happening in terms of snowfall rate or the warming, ice albedo feedbacks are still happening, and so on. So, the most difficult question then is, how is global warming going to affect the natural modes of variability? How will El Nino change? How will Pacific Decadal Oscillation change? How will North Atlantic Oscillation change? How will monsoon change, and so on? So, that is a much more difficult question, and we will keep looking at what changes are happening. We will come back later on to how natural modes may be changing. So, we will come back and continue this. See you next time.